Okay, so for our notes, you need to have I'm using a blank sheet of paper, but you could have lined paper. We're going to title these Unit. And the words I'm going to write in black, and then I'll do some color coding as we go along, so you can do that as well if you'd like. So Unit 1, and we're going to call it Chemistry of Life. The unit as a whole, just to give you an idea here, unit at a glance, we're going to talk about this first topic in this video, the structure of water and hydrogen bonding. And then we're going to look at different elements and then the different biological molecules, and then the properties of those molecules, and then how the structure meets the function and helps with the function of those molecules. And then we look at nucleic acids. So that's the first unit. So we're going to do topic 1.1 today. So for this unit, there is some background knowledge. So the AP curriculum assumes that you've had chemistry and that you remember some things from chemistry. So I'm just going to give you kind of a list of some of the background knowledge things, and then you can look in chapter 2. In our book, it's section 2.1, so the 2 means the chapter, 0.1 is the first section. So 2.1 to 2.4 goes through some basic chemistry review. What kinds of things are in there that you might need to know, as what an atom is and its parts. Valence electrons and what that means. What an isotope is. Energy levels and how they fill up with electrons. Just basic. Let's see, let's put over here covalent and ionic bonds. All right, and chemical reactions. So those are things that you may want to spend a little bit of time reviewing if you don't feel comfortable with what you remember on that. So in that unit, unit 1, we're going to look at topic 1.1. So I'm going to kind of correlate it with the AP guides. So this is topic 1.1 is the structure of water and hydrogen bonding. That's what it's called. And there are, with this topic, so this is what the whole thing is going to be about. With this topic, there's a learning objective. And for this one, there's only one learning objective. Sometimes there will be multiple learning objectives, but there's only one here. And let's write down that learning objective. That helps us to kind of keep the idea of what we're supposed to be learning here. So maybe for the topic, maybe we should underline that. That's our big picture. And so the learning objective. And from now on, I'm going to put in parentheses LO. So whenever we see LO, that is going to stand for learning objective. So our learning objective is to be able to explain how the properties of water I'm just going to put H2O for water. Explain how the properties of water that result from its polarity and hydrogen bonding affect its biological function. Its biological function. So that's what we want to get out of this. All right, so let's look at our first thing about water. Let me move this up here. All right, so underneath this topic here. So one, we want to know, we should know that water is made from hydrogen and oxygen. Its molecular formula spelled that wrong, got a little ahead of myself, is H2O. So now I'm going to start doing some colors here to just show you and make sure that you understand. So let's see, I'm going to get, let's see, an orange, I'll get a green, let's see, I'll do a yellow. So I'm going to use these three colors. And so I'm going to go ahead and draw oxygen. So this is old school, where you have the nucleus in the middle of your atom, and oxygen has 8 electrons, 2 in the first energy level and 6 in the second. So I'm just going to draw that here. And so 1, 2, 3, 4, 5, 6. Remember the octet rule. The oxygen needs 2 more electrons to have its outer energy filled. So oxygen bonds with 2 other elements. I'm going to underline the O in H2O to show that this is my oxygen atom. And then my hydrogen, let's do hydrogen in green. My hydrogen, if we look at the periodic table, it only has 1 electron spinning. So it also has a nucleus, and that 1 electron is spinning in the first energy level here, and it's going to share that 1 electron with oxygen. Oxygen is going to share one of its valence electrons, the electrons in the outer shell, with hydrogen. So now this is filled for hydrogen, and this is almost filled for oxygen. That's why oxygen needs to bond with another hydrogen. And now the 2 hydrogens are fulfilled and the oxygen is. And so this is your H2O molecule. And so this right here is a bond between, and it's a covalent bond between your 2 atoms. And so when you draw, if we were to draw it like this, so this is one way to draw it, and you could draw it like this, oxygen with your 2 hydrogens, like this. Whoops, I switched colors on us here. The 2 hydrogens like this, I'm going to do back that in green. All right, and then these 2 dots, the sharing of electrons, would be the bonds that we represent. This right here, when we draw the lines, represents a shared pair of electrons, which is this and this, are those 2 bonds. And so let's go ahead, I'm going to go back to my black and write some things to the right of our picture here. So although the electrons are shared, between O and H, they spin around O, or oxygen, more. I'm going to put in parentheses, we would say that they are unequally shared. So what does that mean? So since electrons are negative, and from now on when I write electrons, I'm going to put E with a negative sign there, so you know my shorthand. Since electrons are negative, Oxygen has a slightly negative charge, and hydrogen has a slightly positive charge. So let's look at this picture here. So I drew this, it kind of looks like they're sharing equally, but oxygen, since it is a bigger atom, it draws the shared electrons closer to itself, and since these are negative, oxygen has 2 more negative charges that are spinning around it more often, so it has a slightly negative charge. The hydrogen usually has 1 electron, and it now has another one, but that 1 electron that it has is actually spinning around the oxygen more than it would be if it was just by itself. So due to the loss of the negative electron, the hydrogen has become slightly positive. All right, and so we could say that water is a polar, new vocab, polar molecule. Opposite ends have opposite charges. So if we go back up here, I did the bonds with orange, so I'm gonna take my orange here. So this, one of the things up here I talked about was reviewing what a covalent bond is. A covalent bond is when 2 atoms share electrons to form a molecule. And so here we would call this a polar covalent bond. Polar means that the electrons are shared unequally. All right, they're unequal electron sharing. So covalent, they're sharing, polar, unequally. What that does is going to give, let me pick a different color here, I'll do purple, the oxygen a slightly negative charge, and the hydrogen a slightly positive charge. So if I were to do that on here, this is a slightly negative, slightly positive. So so it's like a little magnet, opposite charges on either side. And so the fact that oxygen pulls electrons, draws electrons towards itself, we would say that oxygen is what we call more electronegative. I don't know if you've ever heard that word before, but they spin around oxygen more. All right, so right here, that gives it the charge. And so I'm going to put over here that oxygen is more electronegative. This word will come back throughout the course. So we'll be using it on and off again. So the fact that water is polar is huge in giving water all of its properties. I do want to point out real quickly what it means if you don't have a covalent bond. The opposite of a polar covalent bond is a non-polar covalent bond. So I'm just going to write over here just so that we can know, because again, non-polar things we'll talk about throughout the course as well. All right, so let's write here a non-polar molecule is a molecule in which their atoms share electrons. Again, shorthand, share electrons equally, resulting in no charge. All right, no charge is the key for nonpolar molecule. All right, so let me give you an example. Usually things like oxygen. Oxygen is O2. It's two oxygen atoms double bonded together. Double bonded means instead of one pair of electrons they're sharing two pairs of electrons. These are equal sharing. Why? Because they're the same type of atom, oxygen and oxygen, so therefore they will be equally electronegative, and so one is not pulling the electrons closer to itself than the other, and so these guys would be sharing it smack dab in the middle, kind of between them, and so there would be no charges. All right. Alrighty. So the fact that water is polar. All right. So let's go ahead and write some more things down here. Continuing on back with water. So since water is polar, they are attracted to each other and form hydrogen bonds. I'm gonna, when I write hydrogen bonds from now on, I'm going to shorthand it H bonds. So I'm going to put the key here. If that's going to confuse you, these are your notes. You do you, and so you can write it out. All right. So let's look at this. So if I were to just draw the water molecule, so here's one water molecule. All right, here's another water molecule. Here's another water molecule, and let's do one more. Let's do another water molecule. All right, so when you have, if this is like in a glass of water or something like that, and you have this, these water molecules, because they have the different charges, the oxygens are going to be negative, the hydrogens are going to be positive, opposite charges attract. And so what's going to happen is the negative oxygen of one water molecule is going to be attracted to the positive hydrogen of another. And so that attraction, our book and other places are often represented by a dot, dot, dot. All right, so I'm going to put here dot, dot, dot. So then this oxygen can actually be attracted to two hydrogens. So I'm going to put here at once. Each of the hydrogens can only be attracted to one oxygen. And so so then I can do here, all right, positive and negative. And we could go ahead, we could draw that on here. We could say this is positive and this is negative, negative and positive, just to reinforce its opposite charges that are attracting. And so these right here, let's draw this as a hydrogen bond. Again, I'm going to abbreviate H bond, and that's an H bond between, hydrogen bond between two water molecules. So what I want to show you is that it's actually between molecules. So I'm going to go ahead and take like kind of a pink color here. This is one water molecule. This is another water molecule. This is another water molecule, and this is another one. We have 4 water molecules here, and they're all attracted to one another like this. All right, and they're attracted to each other through these H bonds. So that's what I'm talking about here, where hydrogen bonds are between water molecules. That is different back up when we talked up above about the covalent bonds. So if we look at this one water molecule, this is a covalent bond holding the atoms together to make up your one water molecule. So covalent bonds hold and make up a molecule, and hydrogen bonds are between molecules. So let's write a few words that have to do with that here. So the word intramolecular bonds. What does that do? Holds atoms together that make molecules. So in our example here, for the intermolecular bonds, it would be covalent bond. That's different than the hydrogen bonds. The hydrogen bonds are intermolecular, between molecules. Forget the word, between two molecules. And the example there would be the hydrogen bonds. Okay, so I'm going to switch to a different page. So the fact that water can do this, it's polar and can make hydrogen bonds, gives it lots of unique properties that are important to living things. So that's what we're going to look at next. All right, so let's go over here. This polarity that we just learned about, this polarity and ability to hydrogen bond, again shorthanding hydrogen bond, gives water unique properties. So let's talk about the first one. So some of these you may have heard of. Cohesion is the first one. And let's write the definition between that. This is the attraction between like molecules. The key word is like molecules. What I mean by like, the same type. So our example is the attraction between water to water. All right, now why is this important to living things? All right, so the example is bullet one. Why is this important to living things? I'm going to give you an example. This helps transport water against gravity in plants. I'm going to draw a picture in just a second after we go over the next one. All right. The next one is adhesion. So adhesion, let's write the definition. This is the attraction between unlike molecules, opposite of cohesion. Attraction between unlike molecules. So, bullet here, example here would be water attracted to plant cell wall. Okay, so these two have to do kind of together. Let's just go over here. Here's your big tree. Let's go over an example here. Here's a tree. You're going to learn that I'm not the best artist here. These are your roots. All right, so these are your roots. And I'm going to use orange here. And water is in the ground. Water gets absorbed by the roots and has to travel all the way up to the top of the plant, to the leaves, which is where the plant is going to use water to do photosynthesis, which is making food for the plant so the plant can grow and live and so on. All right, so how in the world does this get up to there? Well, there's a tunnel system of cells. So I'm going to enlarge this part here, and it's a whole big column of cells. So I'm going to go ahead and draw a column here. And the cells are long, and the ends of the cells, so this is going to be many cells. The ends of the cells have little holes in them, and they're kind of like this, and they're at a diagonal like this. So what you're looking at is a cell. This is one cell right here. This is a cell right here. So you've got this whole system of cells, and this is a cell right here. And so this is, water is going to be coming from your roots and has to travel up this. And so it's, you can have a 50-foot tree. It's a really big deal to get the water up there. So how does it do that? So for water, let's get a different color for water. I'll use purple. And so I'm just going to go ahead and draw some water molecules in here. So I'm going to do an H2O with two H's. All right, and then I'm going to do another H2O like this. All right, and another one like this, and another one like this. Okay, now, so I just drew 4 H2O molecules. So what are they going to do? They are going to hydrogen bond to each other. So between the oxygen and the hydrogen, there's going to be some dot dots. All right, so I'm going to use red, and I'm going to do dot 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 all of the between the oxygen and the hydrogen of each of the molecules. So this one's attracted to this one, which is attracted to this one, and so on. So you kind of get like a train of water molecules all the way up. All right, and so so what happens here is that's thing 1. All right, that is hydrogen bonds, which in this case here, the fact that the water can hydrogen bond gives it cohesion, attraction between like molecules. So because of that hydrogen bond, we get cohesion going on. All right. The other thing that you can't see here is that the oxygen is also attracted to the cell wall. All right, so therefore you do have some attraction here to the oxygen to the cell walls. All right, so I'm going to write here that I'll just put that the water is attracted to the cell wall. And that is adhesion. So you have cohesion and adhesion going on to help the water move up. I'll show you also a little video that shows like that water evaporates from the leaves, and when the water evaporates from the leaves, it pulls the whole chain of water molecules up, and so then that's how water travels up the plant. All right, but in fact, it's due to both of those things, cohesion and adhesion. So let's see here. Let's do C. We were on B. Let's do C. Is surface tension. So surface tension here, let's define it as a measurement of how hard it is to break the surface of a liquid. All right, so what happens is that when you have water molecules, let's say our paper is the surface of water. So let's draw here the hydrogen bonds between them. Let's say these guys here, they're kind of far apart, but you get the idea here. All right, if I were to be something that can spread my weight over a large surface area, then some things, if you were to set it on the surface of the water, would not break the hydrogen bonds. Their weight distribution would not be enough force to break those hydrogen bonds, and they can actually float on water. All right, so this is why some things can, like an example, there's a bugs called water striders, can walk on water. Because, again, they've spread their body weight over the surface and do not break those hydrogen bonds. So that creates something called surface tension. All right, let's go to letter D, high specific heat. The amount, let's go ahead, amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. To change its temperature by 1 degree Celsius. All right, so what does that mean? So, some things have high, some things have low specific heat, and it's specifically talking about how much heat needs to be absorbed or lost to change that temperature by 1 degrees. And so water's is high, it has a high specific heat. So because water specific heat is high, high is the key word there, it minimizes temperature fluctuations to within limits that permit life, since we're talking about biology. Limits that permit life. So let's put here an example. Living things, cells are made up of, or let's say living things. Living things are made out of cells. Cells contain a lot of water, all right? Are made of 70 to 95% water. Cells are, depending on the type of cell. Whoops, I just said what cell and wrote it down. 70 to 95% water. And so what it does, it helps to moderate the temperature of living things. So what does this mean? Temperature of living things. So we can absorb a lot of heat, and because we're made up mostly of water, we don't heat up really fast. So because water has a high specific heat, which means that you have to absorb a lot of heat in order to raise the temperature of water 1 degree Celsius. And so it helps living things not to heat up, or on the flip side, cool down too fast. And so there's one other example I want to put here, but I ran out of room here. So I'm going to go to the next page and put a third bullet here, kind of indented, and put another example. And that's with lakes. Lakes can absorb a lot of heat from the sun without heating up too much for the organisms that live in it. So, organisms. So, you don't have a lake, the UV light pounding on it and beating on it all day, every day during the summer, and it doesn't start boiling or anything like that. All right. So we were on letter D. We're going to go through and do letter E. This is the high heat of vaporization. All right, let's do a definition there. This is the heat a liquid must absorb for 1 gram to be converted to gas. Liquid to gas, what is that? Evaporation. And one thing that's, because of that, it has a high heat of vaporization, which means that it has to absorb a lot of heat before the water molecules my hands are water molecules and they're hydrogen bonded to each other, they have to absorb a lot of heat, and then they get more kinetic energy, moving and moving and moving, and you have to absorb more and more and more heat until finally they have enough energy to break that hydrogen bond and evaporate. All right, and because the molecules that are evaporating are high in energy, they take heat with it. So let's write that as. So why is it important for living things? Is as a liquid evaporates, its remaining surface, the surface that was on, cools. This is called evaporative cooling. I'm gonna underline, that's a vocabulary word. So think about, this is why we sweat. So we sweat, we get water on our skin, and then when that water evaporates, it cools the surface that it is evaporating from, and so it cools that surface off, which in this case is us. So anything that we can do to increase the speed at which the evaporation occurs will make us feel cooler faster. So think about when you sweat and you stand in front of a fan, then you feel cooler much faster than when you are not standing in front of the fan, because it's sped up the rate at which evaporation occurs. If you are in a high humid day, like in Michigan, the summer can get pretty humid, that means that there's a lot of water in the air, and it slows down the evaporative process, and we don't feel as cool as quickly. All right, so then letter F, the fact that ice floats. So we all know that ice floats. All right, and why does it float? The solid water is less dense than liquid water. So why is that? All right, so let's look at this. As water cools from 4 degrees Celsius down to 0 degrees Celsius, the water molecules move too slow to break the hydrogen bonds. So they slow down, it's cool, they slow down, so they're not moving as fast. In liquid water, they're moving a little bit faster, so they can break and reform hydrogen bonds a lot, but not when they slow down. And so, let's write at 0 degrees Celsius, they get locked into a crystalline structure. And so I'm going to have you refer to page 35 in your textbook, figure 2.2. And so let me display that for you. Okay, so over here is liquid water, and you can see here the water molecules are closer together. Liquid water, they're going to be moving faster, and they will be breaking those hydrogen bonds and reforming them, all right, so that they are liquid, or so that it has a liquid property. When the temperature gets closer to 0, they slow the movement down, and because they hydrogen bond, those bonding forms specific angles that makes this crystalline structure. And they're not moving fast, they don't have enough energy to break those hydrogen bonds, and so you can see that they are spaced out. And so if this circle and this circle are the same amount of space, if we counted up how many water molecules are in this space versus this space, there's more water molecules here than here, which is what density is. And so you would have more mass per volume here than you would here. So ice is less dense as a solid than as a liquid. Let me go back to the page. Okay, so that's what figure 2.2 is showing you. And what that does is why it's important to living things is it insulates bodies of water. All right, and allowing life to live underneath there. So think about this. If this is your water, and you have little fishies swimming in the water, and this is your bottom of your lake or whatever. If ice froze from the bottom up, poor little fishies are going to die. All right. So what we have instead, here's your bottom of your lake. Here's your fish. All right, and here's your water, and then as it cools, it forms this floating ice. It's floating and creating a barrier between the cold air above and the water below, and it doesn't let the water, that barrier of ice won't allow this water underneath to get so cold that it will actually freeze. And so therefore that's what we mean by insulating the body of water so that the fish will survive the winter. All right, and the last property is that water is what's called the solvent of life. Some definitions here. All right, so what is a solvent? So solvents make up a solution, or part of a solution. So a solution is a liquid that is a homogeneous, meaning it's evenly mixed mixture of substances. Here's where underneath here, solvent, hence the name solvent of life. Solvent is the dissolving agent. What's doing the dissolving of a solution? And a solute is what's being dissolved. So water is a great solvent. All right, so why? Water is a versatile solvent due to its polarity. So versatile means it can dissolve many different things. All right, so what kinds of things can it dissolve because it's polar? So remember, it's polar because it has charges. So therefore, there's an old saying, like dissolves like. So water, which is charged, has polarity, can dissolve other polar substances. So it can dissolve other charged substances. So what are those? So example one would be other polar molecules. Example two would be ionic substances. So we didn't review what an ionic bond is, but I had said that you should review what an ionic bond is. All right, so ionic substances are substances that are charged, like NaCl, salt. Two ions, charged molecules that lost or gained electrons, This one has a positive charge, this is a negative charge, positive and negative attract, and so these guys are not sharing electrons, they are just attracted to each other because of their opposite charges. And so this right here, these two, since they can be dissolved in water because of their charges, we could also say another word for these collectively is they are hydrophilic molecules. All right, what does that mean? They have an affinity or attraction. So if you don't know what affinity means, go ahead and write attraction. All right, have an affinity for water. So literally, and hydrophilic literally means water loving. And we can look for these two to give you an idea of the figures. There are two figures in your textbooks, figure 2.21 and 2.22. All right, where you can look to see it dissolving those substances. Let me pause it and I'm going to show you the picture. So this is a picture of water dissolving salt. So here's you got your beaker with a chunk of salt. So here's your chunk of salt. That chunk is going to have many of those NaCl molecules. So you can see here the positives would be the sodium and the Cl is the chlorine. And the water molecules are going to come over here and surround the different charged particles and kind of break them away from the larger crystal. And so you can see that this has happened already to one sodium and one chlorine. And notice that the sodium here are surrounding the water is surrounding the sodium, and notice, because sodium has a positive charge, notice the negative oxygens surrounding it. That's called a hydration shell. Hydration is because it's with water and they're literally forming like a little shell around it. And so this sodium can no longer bond to this chlorine anymore, or any of the chlorines in here, because the water is literally surrounding it. The same thing with the Cl, and so you have here all the positive hydrogens. You see how they're oriented around there, around the Cl, and therefore no other thing besides the water molecules can get to it. And so therefore that's what dissolving is. So it's taking this ionic substance with all these ions stuck together in this big chunk, and if you let this sit, even if you don't stir it and you let it sit over time, eventually that chunk will be gone, because those little water molecules will keep on picking away at this and surrounding each one of the ions, and eventually you'd have all the ions equally spread out throughout your water, and then you wouldn't see the solid at all. That's your ionic substance. And so I think it's figure 2.22 shows you a polar molecule as well dissolving, and you can take a look at that. And then lastly, let's write what water does not dissolve. So water does not dissolve things with no charge. So what does it mean by things with no charge? All right. So water was a polar molecule that had two different charges on either end. Remember, the opposite, going back to the first page, is a nonpolar molecule where there's no charge. So with no charge, this would be like a nonpolar molecule. So what would be an example of that? Oil. All right, oil does not dissolve in water, and it will separate out and not dissolve in it. Another word for this, things with no charge besides nonpolar, opposite of hydrophilic is hydrophobic. no affinity for water. And this word literally means water-fearing. So those are some properties of water, all because water is polar and can hydrogen bond. All right, so this is where I am going to stop the video. See you in class.